Guilty abamfanabo. So welcome to Science Intellect Hub. My name is Mr. Mojakisane Se. They call me Mr. M Mfanabo. So halala right now. Well, remember that in our previous session we said that if this is a chemical change, when a chemical reaction happens, chemical change occurs. So that is why we said chemical change, chemical reaction, same shit in Fanabo. So, well, we said then this will be our system of consideration, if you recall. And outside the system, we will have the environment. And what we said is that we will need energy somehow from somewhere in order for us to break the reactants so that we can do what? So that we can form new products in Fanabo. So that is what we said in our previous session. And we said, well, the environment, in actual fact, what it does is that it provides energy to the system, meaning the system absorbs energy to break the reactants in the products. And at the end of the day, then we will have products releasing energy to the environment. That is what we said, releasing energy to the environment. And we said then we have two types of chemical reactions that can occur, of course. We have what we call an exothermic reaction, and we have what we call an endothermic reaction. So whether we are having an exothermic or we are having an endothermic, one thing for sure, energy will have to be absorbed and energy will have to be released. Now, depending on how much needs to be absorbed by the system, then we can talk about exothermic or endothermic. And also depending on how much was released by the system, then we can talk about an endothermic or an exothermic reaction. So, halala right now. Well then, we've differentiated between an exothermic reaction versus an endothermic reaction in our previous session. We said, well, when we talk about an exothermic reaction, overall energy that is released is more than energy that is absorbed. So for this reaction then, overall we say energy is released. So check, that is an exothermic reaction. And when we represent it chemically, we will write reactants giving us products and we say plus energy, whereby that plus energy implies that for an exothermic reaction, energy is being released. So the other thing that we said was that the heat of reaction, or delta H, is less than 0 for an exothermic reaction. Then when we consider an endothermic reaction on the latter, then we can see that in actual fact, overall energy has been absorbed. So that is why when we write reactants, we say plus energy, because more energy has to be absorbed than energy that will be released. So therefore, at the end of the day, for an endothermic reaction, we say energy is being absorbed, and our delta H here, which is our enthalpy, our heat of reaction, is greater than 0. So today's session is mainly interested then in us trying to make clear what we mean by the concept of enthalpy through analyzing what we call energy profiles. So halala right now, let us have a look at the energy profile of an exothermic reaction. That's what we want to be looking at this particular time and moment. Well, what you'll recognize about the energy profile is that it is a graph, of course, showing us the potential energy as time goes, meaning the potential energy of the reaction as time goes. And we can see that indeed the potential energy, of course, is time dependent in this particular time and moment. It is the dependent variable, whereas time is the independent variable. Well, otherwise Ardaso. Where we are is to have the ability to analyze as to what is happening in this reaction. First and foremost, what we'll recognize is the fact that the units that we use for potential energy is definitely kilojoules. kJ? Nope. kJ. Yep. So we want to ensure that the units for kilojoules, for J, of course, we have capital letter J. Why? Why capital letter J? That is because we are giving a credit here to one of the best physicists here called James Prescott Joule. This man has done a lot of research when it comes to heat and energy. Things like the principle of conservation of energy, and something that is called mechanical equivalent when you go to thermodynamics. Remember, what we are busy with at this time and moment is chemical thermodynamics, not thermodynamics specifically, but chemical thermodynamics. So every time we hear the word thermo, we know heat is going to be involved, come hell or high water. So we are happy with the fact that then potential energy is going to be measured in kilojoules. Check. Another thing then that we want to discuss, of course, as we go on here, is to have a look at what is happening here. Maybe let us change color to blue here. Look at where the energy of the reactants is located, around 20 kilojoules. And look at where the energy of the product is located, around 10 kilojoules. That's very important. It is very important when you consider the energy profile of an exothermic reaction, that you are able to know where is the energy of the reactants. In this case, 20 kilojoules for this hypothetical example. Where is the energy of the products? According to the potential energy, it is at 10 kilojoules. Good job. But for now, we will be interested in a few things, of course. The first thing that I want us to be interested in is to go back to when we were talking about enthalpy. Do you recall that at this time and moment we said delta H, which is enthalpy, that is the heat of the, or the energy of the products minus the heat or the energy of the reactants in this particular time and moment. So when you look at this graph, because we have numerical values for the potential energy, we can be able to calculate the enthalpy of this particular reaction. So therefore, our energy of the products, as we have said, it's 10 kilojoules. So we will write 10 kilojoules minus the energy of the products, there it is, or rather of the reactants, there it is, 20 kilojoules. So we will have 10 minus 20, which gives us negative 10 kilojoules. Well, the fact that there is negative there is very, very pivotal to us. It is a reminder that, remember, when we talk about an exothermic reaction, we know for sure delta H will always be less than 0. That is what we've said so far about an exothermic reaction in the previous session, where we said, of course, indeed, what we have is that delta H will be less than 0. So, halala, right now. So we have proved then through calculations that indeed delta H is less than 0. Halala, right now. So I want to clean here a little bit and discuss a few things here. Now I've proved to you why we said for an exothermic reaction, a delta H is less than 0, or enthalpy is less than 0. Let me have a sip of coffee here. A good job. Now, let us continue, of course. We can see something very strange when we try to analyze the energy profile of an exothermic reaction. Look at the energy of the reactants there. There it is. It is a straight line. That's understandable. Look at the energy of the products here. It is also a straight line. But why is the energy picking up and down as we go through here? Why is that the case? Why is it that energy is being shooting up here, then after that it shoots down? We have to ask ourselves of such questions. Why is that the case then? When we look at an energy profile. Well, I said for a chemical reaction for which an exothermic reaction is part of. When you consider a chemical reaction, we know energy has to be absorbed from where? From the environment. So energy is being absorbed from the environment. So whether we are talking about an exothermic or an endothermic reaction, we see that we are having this curve. That is because energy has been absorbed. And then we reach this maximum state of reaction. We will talk about what is that maximum state of the reaction, whereby the energy is at its maximum. We'll talk about what is that. But now, as reactants form products, remember we have used energy from the environment to the system. And what happened? The system has absorbed energy to break atoms of the reactants in order to do what? In order to form new products. As new products form, energy is being released. But look at how much of energy is being released here compared to how much energy is being absorbed. So we can see for an exothermic reaction, so very little is absorbed, but so much is released at the end of the day. That is why, after all, for an exothermic reaction, we have argued that overall energy is being released. You can also see that and prove that through the energy profile of an exothermic reaction. So halala right now. Well, so far we've only looked at the energy profile of an exothermic reaction. How about now we look at the energy profile of an endothermic reaction? Well, one of the distinguishing factors about an endothermic reaction is that, of course, delta H is greater than 0, meaning enthalpy is positive, meaning the heat of reaction will be a positive number. So halala right now. Now remember, zange exam so njalo nje. What they will say, they will tell you, or they will tell you to tell them. That's what they will do. They will tell you to tell them whether the reaction that they've given you is an exothermic reaction or it is an endothermic reaction. And of course, if it is an exo, you must tell them that it is an exothermic reaction. But they will say, explain your answer. How will you do that? This is where you will go to the enthalpy and tell them, because the enthalpy is negative. But for an endothermic reaction, you'll tell them that it is an endothermic reaction. Why? Because delta H is greater than 0. Delta H is a positive number. So halala right now. Now if you look at the energy of the reactants, there it is there. It is a straight line there at around 10 kilojoules. Whereas when you look at the energy of the product, there it is around 20 kilojoules. Now, if you recall, we had something like this for the energy profile of an exothermic reaction. It was something like that. I'm a physicist and a chemist. Please forgive my artistic skills. not that good. So this is how, of course, our exothermic was looking. The red color there. Good job. But Arida, where we are at this time and moment, of course, is strictly understanding an endothermic reaction. One of the ways, of course, will be to calculate delta H. How about we try that for now and calculate what? Calculate delta H. Well, we know that delta H, the heat of reaction, is the heat of the products or the energy of the products, and we subtract the heat or the energy of the reactants, and that is going to be, if you check the energy of the products, there it is there at around 20 kilojoules. We subtract energy of the reactants, there it is there at around 10 kilojoules, and it makes sense then that we are ending up with a positive value of 10 kilojoules. Good job, mfana boss. So halala, right now we are moving at 120 kilometers per hour. Remasse blind. So we can see in this example here, why is it that for an endothermic reaction we end up with a positive value? We've proved that through calculations. Good job. Now I want us to look at another concept, of course, which is that we've already mentioned about the absorption and releasing of energy. Now, if you check here, after the reactants were not gonna react to form new products. The reactants were not gonna break to form new products unless, of course, the energy was provided by what? By the system. There is the system, it has provided energy, hence the reaction has absorbed the energy. And I've already told you that the energy absorbed by an endothermic reaction is greater than the energy absorbed for an exothermic reaction. That is why overall, when we define an endothermic reaction overall, we say energy is being absorbed. Good job, mfanabo. So halala, right now energy is being absorbed. Now as energy is being absorbed, we will reach the maximum state of the reaction, which will be somewhere here. Remember, the maximum state of reaction, we'll talk about it. That is where the reaction is at its most unstable state. It is where the reaction's energy is at its maximum. Now upon reaching that, meaning after reaching that, then we expect a decrease in energy until new products are formed. Now comparing the energy absorbed versus the energy released, you can see that indeed, holy shit, more energy has been absorbed compared to the energy released. Good job, mfanabo. So halala, right now mfanabo. So let us conclude our theory by talking about the concept of activation energy as well as activated complex. Well, maybe what we want to do is to ask ourselves, what type of reaction is this one? Is it an endothermic, or perhaps is it an exothermic? Well, you know one thing for sure, that whenever delta H is less than 0, meaning delta H is negative, we are talking about what? We are talking about what we call an exothermic reaction. Good job. So this one will be an exothermic reaction. Whereas on the latter, because we are having delta H greater than 0, then we will call that an endothermic reaction. Check. Good job, mfanabo. So halala, right now. So from here then, we want to talk about the concept of activation energy. By definition, when we talk about activation energy, we say that it is the minimum energy needed for the reaction to take place. Bazo zange exam mfanabo. So injalo nje, you must be able to tell that activation energy is the minimum energy needed for the reaction to take place. Do you remember I said that the system itself needs to absorb energy? This is where it absorbs. It needs to absorb energy, be it we are talking about exo or endothermic reaction. There will be some bit of energy absorbed. Now that energy will be absorbed, then what do we think will happen from thereof? Something interesting is going to happen. As energy is being absorbed, remember that energy is being absorbed to break atoms in the reactants so that we can form new products, right? So it means in this case then, after energy has been absorbed from the system, or rather after energy has been absorbed from the environment, then we will reach this state here, which is the activated complex. And if you can check something about the activated complex, energy is at its maximum here. That is because by definition, when we talk about activated complex, we say that it is the unstable transition state. Before we continue, when we say that it is an unstable transition state, we are saying that of course it will be where energy is at its maximum, because this is unstable. So it is an unstable transition state from the reactants to products. And one thing for sure about an activated complex is that energy is at its maximum. So now what we will also recognize is that this activation energy will always be from where? It will always be from the energy of the reactants to the energy of the activated complex. And when we check also here for an endothermic reaction, the activation energy, which is the minimum energy needed for the reaction to take place, it will be from the energy of the reactants all the way to that unstable transition state, which we refer to as the activated complex. Now, another important thing that I wanted to take into consideration here, Mfanaboso, is the fact that when you look at the activation energy of an exothermic reaction versus the activation energy of an endothermic reaction, we can see that the activation energy of an endothermic reaction is greater, it's bigger than the activation energy of an exothermic reaction. That is true because in actual fact, we said for an endothermic reaction, more energy needs to be absorbed so that the reaction take place. So more energy will have to be absorbed for the reaction to take place. Hence, we have a greater activation energy for endothermic reactions than exothermic reactions. So, welcome to Science Intellect Hub. My name is Mr. Mojaki-san. They call me Mr. Mfanabo. So, halala right now. Well, if you found value in this video, please ensure to like, comment, but most importantly, subscribe. Give me a holla. So in terms of theory, check. What we'll do in our next session, of course, will have to be nothing else but a few questions and examples about this topic. Good job. Till we meet again. Peace.